if both the expectation value and the standard deviation is unknown. Instead of using a normal distribution, one uses a distribution similar to the normal distribution, and that's called a t-distribution. A t-distribution depends on the sample size. So if for the black curve here we have a standard normal distribution, and the other ones here are very similar, and those are the t-distribution for different n values, that is different sample values. And for a t-distribution you talk about the degrees of freedom, and degrees of freedom is n minus 1. So here is the degrees of freedom 0, 1 and 4. However, there's not much difference between calculating with the normal distribution and the t-distribution. The only extra thing you have to keep track of is that you have to know the degrees of freedom. So you also need n when you're reading off the tables. Also for t-distribution you talk about this alpha, but then you talk about t alpha. So it's defined in the same way as set alpha. So t alpha here is the t value that will give the probability here equal to alpha. And then when you check the table, you also have to know the degrees of freedom. But other than that, it's very similar to read off the probability table for set. So let's say that we want to find what the probability for getting t larger than 1.2, that is t alpha is 1.2, for 5 degrees of freedom, that is n is equal to 6. Then you can look at this t table, and you see here, in the same way as for the set table, here is the probability for t being larger than t alpha is equal to alpha. But now here is t alpha, but in this row here, instead of the 100th decimal, here is now instead given the degrees of freedom. So in our case, we want to find out for t alpha equal to 1.2 and 5 degrees of freedom. So then go from here 5 and 1.2, so 0, 14, 19. So you read off a t-distribution in the same way as for a set distribution. You only have to know also the degrees of freedom. And oppositely, let's say that you know the alpha. So let's say you have alpha equal to 5%. And you want to find out what t alpha is. And let's say that n minus 1 is equal to 10. Then there is a third table you can look. So instead of using the other table backwards, for the t, there's here given a table to read off in the opposite direction. So here we have the degrees of freedom, and here we have alpha. So in our case, alpha was 5%, so we are here, and 10 degrees of freedom. We can read off t alpha as 1.81. So that's how you read off the t table, or two t tables. Otherwise, reading off a t-distribution, working with the t-distribution works in much the same way as for a normal distribution. So assume now we have a random variable where both the expectation value and the standard deviation are unknown. If we made a sample of sample size n, then we have gotten a mean and we have calculated the standard deviation of this sample. So this is not equal to this, but this is the standard deviation of the sample. This is a standard deviation that is unknown, that is for the random variable x. So let's assume that the mean is normal distributed with this mu and sigma. However, but instead of using the standard normal distributed set, which before defined like this, now this is unknown. So now we estimate this with s. And that means that we instead put s here, and this is now called t. And this random variable is t-distributed. And that comes from that both now the mean and s will vary, will be random variables. Then we have the similar result that with the probability of 1 minus 2 alpha, the true unknown expectation value will be in this confidence interval. And if you compare this with when we had a known standard deviation, the only difference here is now we have t instead of set here, and we have s instead of sigma. Assume that in the years 2010 to 2018, the number of lightning strikes in the Empire State Building yearly was given by the following dataset. So in year 2010 was 22 lightning strikes, and 2018 there were 31 lightning strikes that year. Assume that these 9 observations are of a random variable x with an unknown expectation value and standard deviation. We want to find the confidence interval with 95% probability for the expectation value. If you calculate the mean for this dataset, you will get 23 lightning strikes average, and you get a standard deviation of 4.42. So that means that we estimate the unknown standard deviation with s equal to 4.42. Let's assume that this random variable, the mean, is normal distributed. In this case, alpha is equal to 0.025, and we have 8 degrees of freedom. And that gives, from the table here, for 0.025 and 8 degrees of freedom, 2.31. Then the confidence interval is given by this we had here. So if we put in our values, then we get this confidence interval, which is roughly equal to 20 to 26. So that means that with 95% probability, we know that the expectation value, the true expectation value, is between 20 and 26 lightning strikes per year in the Empire State Building. Let x be the traveling time by train if you go from the city Drammen to Oslo. And here, this is the expectation value of x, and this is unknown. And also the standard deviation of this one is unknown. After making 60 trips, we got an average traveling time of 35 minutes with standard deviation of 3.1. Let's say we want to find a 95% confidence interval for the expectation value. That is the traveling time. Since n is larger than 30, then the mean is normal distributed. Alpha is equal to 0.025 with 59 degrees of freedom. Then according to the table, we have that T alpha is equal to 2. Then the confidence interval becomes, which can be rounded off to this here. So with 95% probability, the true traveling time is between 34 minutes and 46 minutes. Then you can ask, how many trips do you have to make if you want to get a confidence interval with a width of 1? Then if you calculate, just as we did it for the expectation value with known standard deviation, in this case we instead get for n. And if we use now the same as we had here for T alpha and s 3.1 and with the width of 1, then we get 154. So if we want the width of this interval to be 1, then we have to make 154 travels. So then you instead get this confidence interval.